So, as the name suggests, we can see that there are two keywords that we have to deal with. One is the network functionality, and the other one is the Laplacian spectra. Those who are comfortable with the theory of graph, they know that this Laplacian spectra basically related to a particular matrix of graph known as the Laplacian of the graph. Okay, but what I will do, I will try to give you some brief accounts of the results or some preliminary results of Laplacian. Then we will try to go into the detail of the measure that is considered for the today's talk. And if you find anything not going in your way, then please stop me and I will explain it to you. Or if you find anything which is not the scope of this particular, should I say, the course of this workshop, then I should skip that part. Okay, and basically my talk will be divided in three parts. First, I will try to introduce few basic idea of the network, especially the complex network. Then I will try to explain few of the results associated with Laplacian spectra and the network criticality. And in the later part, we will see that how this measure is effectively used by some other researchers citing our work in cybersecurity and other issues related to AI. So that is my, you can say, course of this or the flow of this talk. So the outline of the talk will be like abstract, then there will be some introduction, as I have already told you, then preliminaries and network criticality, and the novel measure that is introduced by us, and some application of that measure will be reviewed. And some future course of future course of direction will also be discussed during the what you can say is the concluding part of this talk. So as you all know, with the growing appreciation of complex networks, models of various systems like water supply, energy, communication and transportation, the techniques of network analysis have come to play an important role in the representation and in understanding of the structure of complex network. By complex network, I mean that, as the name suggests, it is something which is complex in nature. It may be evolving in time. Sometimes the network is not regular. In fact, it is not regular in most of the time. That's why I call it a complex network. And the dimension or the topology of the network is also changing over time. So these are some very, what you can say is, these are some very prominent features of complex network. I hope at least some of you are aware of this complex network. At least you have heard about this. So the abstract goes like this. Historically, the study of networks has been mainly the domain of branch of mathematics called graph theory. But in last decades or so, we have witnessed a new movement of interest or research in the study of networks, considering the networks as a complex system. As I have already told you, complex networks are nothing but these are networks which are irregular, complex, and dynamically evolving in time. And network criticality is a measure that is introduced by Garcia and Tisgram to measure the network robustness, which is derived from the probabilistic definition of betweenness. The objective of this talk is threefold. First, we will discuss some preliminaries of graph Laplacian, few known results on network criticality. Second, we discuss a new measure of network functionality. Then we highlight some applications and future directions. And if you find my voice is not audible, so please stop me, because it will not be possible for me to figure it out. Okay, please. At any moment of time, if you find my voice to be not audible, then please stop me there.
Okay,
Okay.
sir.
Okay. Thank you. So, before going into the introduction, what I should say is that I want to basically highlight two papers, two seminal papers, which were published in the year 1998. The first one that I am considering is the paper published by Wattstroges, and the second one, which is published in the year 1999 by Baravasi Albert. It should be Barabasi. There is a mistake here. Okay. And you can see the number of citations that these papers have received over the years. So that speaks for the amount of work that has been done and that is going on this particular topic. Why this topic is attracting so many researchers? Because of its dimension. We have found that the complex networks have been used. The theory of complex networks have been used almost everywhere in the various branches of science as well as social sciences. In fact, so the sociologists find it very interesting to analyze the social networks like Facebook, Twitter, and all. And I'm sure that many of you are aware of this fact, and we will try to deal with the network theory that will help to understand the function and evolution of complex networks. So it is not possible for me to deal with all the properties and functions which are useful in the theory of complex networks, obviously, for this small period of time. So what I will try to give you a glimpse of that. So let us start the discussion with some examples. So this is our very own internet, the World Wide Web, we can also call it, and that can be modeled using complex network. This is status communication network. The next one is contagion tuberculosis network. So you can see I am citing the papers from where I am taking this particular figure. So if you are interested, you can go through that particular paper and you will find the detail of this, how this network is constructed. So basically, these nodes are selected. By node, I mean from the theory of graph, these are nothing but the vertices. Okay, so the vertices will be replaced by nodes in the theory of networks, and edges will be termed as links. These words are synonymously used. No issue on that. Okay, and this is the metabolic network, protein interaction network. Then we have Airport Network of India. So this figure is taken from one of our paper. And this figure, maybe I have taken this figure from the paper of Newman, where the various structure of complex networks have been discussed. There, Newman has broadly divided the various complex networks into 4 categories. We would like to call it bits. B for biological network, I for information network, T for technological network, and S for social networks. So these are the broad 4 categories, based on which we can divide or we can categorize the entire set of complex networks. Obviously, as the name suggests, in case of biological network, the nodes will be something like metabolic proteins, links are chemical reaction, interaction. For an infrastructure network like this, or railway network, or there the platforms, there the airports will be considered as the nodes, and the connectivity or the, say, the number of flights per week, something like that, will be considered as the link. Similarly, for other networks, say social networks, all the users will be the nodes, and say friendship can be considered as a function of link, based on which you can define a link. So this is a very, what you can call it, a uh, very preliminary introduction to complex network. These are the four categories. And in case of complex network, what is found that there is always an issue with the attack. Whether we are considering a topological whether we are considering uh, a transportation network, or we are considering a biological network or a social network or an infrastructure network, there is always an issue with the some malpractices, some tampering, or some changes that may occur at different places and different parameters in those networks. And the robustness is the criteria, or you can call it the concept that will basically judge the network based on its reaction to those changes. So if I want to define it formally from the control theory point of view, robustness is the capacity of a network to keep itself in stable mode when changes take place in different parameters of the network due to uncertainty. And what are the kind of changes that we can expect in a network? So we can divide the kind of major changes into three parts. I mean, three categories. One is the changes in the network topology, where there may be some changes in the layout of the network, there may be some deletion of node, there may be some deletion of link, so on and so forth. And in the second one is the community of interest. So some new links may be developed, some earlier links may be removed. So that is basically the interaction or dynamical behavior of the community present in the network. Or I would like to call it active source destination pair. It's an interaction between source destination pairs. And the last one is the traffic demand. Sometimes the link may not be, rewired, but we have to increase the load in the network in that link. That is also a change. Okay, that kind of change also may occur because of the demand of the network. I think we can very much understand these three changes, and we can relate to our day-to-day life where these changes can occur in a network. So throughout our discussion, we call a network robust if its performance is not sensitive to changes in these three categories. I mean, topology, traffic, or community of interest. Okay. Now let us go to the measure that we are going to uh, use in the to define our measure, that is the network criticality. So notion of network criticality was first proposed by, as I have already told you, by Dibrugarh and Leon Garcia in 2008. So it is a robustness metric to capture the effect of the changes such as traffic variation and topology changes in the networks. So here you can see that the main point that you have to be very sure about is that this measure is a global measure. That means for a network we will have only one value of network criticality. And as the name suggests, if we have higher criticality, the network will be less robust. That is for sure, right? That's why this is called network criticality. how critical is the network. This parameter will basically determine how critical is the network or how vulnerable is the network, if I want to call it in from the network scientist point of view, how vulnerable is the network to various changes. Okay, so if we have less value of network criticality, then better will be for the robustness. And a network is basically, as I have already told you again, the nodes are some places, some persons, some proteins, and the reactions are, or the interactions are the link. So in that way, we can always model a network using weighted graph. And network criticality is defined as the average random walk betweenness of a link normalized by equivalence. So I will discuss these technical terms in the later slides, but for the time being, just I want to mention that network criticality is basically the average of random walk betweenness. So it is something to do with the betweenness. So when we will introduce the term betweenness, then it will be clear for you. Okay. And they have found that, interestingly enough, this network criticality, this Allen et al. In 2011, is actually related with the Laplacian matrix. So, as a theoretical person, we are more interested in this kind of result. For application purpose, this parameter was defined, but theoretically it is found that this guy, I mean this particular element, this parameter is actually equal to twice n plus L plus. So what is L plus? L plus is the Moore-Penrose inverse of the Laplacian matrix. What is Moore-Penrose inverse? It's basically a generalized inverse. And many of you may know that the Laplacian matrix is singular. So it is not possible to find the inverse of that matrix. So we have to go to the some generalized form of the inverse. We will discuss this Moore-Penrose inverse. And it is to be mentioned that, as I have told you, this is basically a global measure independent of link and node. It is decreasing and strictly convex function of link weight. So if the weights increases, then this criticality will decrease. And for proof of these results, you can consult the paper of the same authors, Gadam and Leon Garcia, published in 2010. So this is a global measure decreasing with which link weights. Basically, that you should understand. Okay. Now, what is Laplacian of a graph? So some of you may be very comfortable with this, but as I am told that all the persons are from, I mean, not from graph theoretic background or from different background. That's why I want to give you some basic idea of the matrix. So Laplacian is basically a square matrix where diagonal entries will be the degree of the vertices. So what I mean by degree of a vertex? Degree of a vertex is basically the number of edges attached to that vertex. And if there is a connection at the ij place, there will be minus 1. I mean, if I vertex is connected with j, then the ij place of the matrix will be minus 1. And it is not difficult to see that this matrix is actually equal to B minus A, where A is our adjacency matrix. This is an example. This is a graph. You can see that in this graph we have 4 nodes or 4 vertices, and that's why it's a 4 cross 4 matrix. Adjacency matrix, we will consider only those connections. If there is a connection, we should put it 1, otherwise 0. And you can see in the degree matrix, the diagonal entries are considered to be the degree of the vertex. So for first vertex, the degree is 2. That's why in 1 1 position we have 2. The degree of second vertex is again 2. That's why we have 2 in the 2 2 position. And the degree of the third vertex is 3. That's why we have 3 in the 3 3 position, and so on and so forth. And if we go by the earlier definition of Laplacian, this will be something like this. L will be a proportional matrix with entries like 2, -1, -1, -1, 2, -1, something like that. And it is not very difficult to see that if we construct the d minus 1, if we compute the d minus 1, that will be equal to the Laplacian. Also, if we observe this matrix, this L matrix, there you may find that sum of each row is equal to 0. This is not surprising, in fact, or this is not a special case, in fact. This is true in general. Why? You see, in a row, you have all those ones corresponding to some, in case of rows of adjacency matrix, you will have ones against every edge. So, if we sum up the rows of Laplacian, that will be equal to 0. So each row of the Laplacian will be equal to 0. From this, what we can conclude is that 0 is an eigenvalue. Most of you may be aware of the fact that if sum of each row is equal to some fixed quantity, say k, then k will be an eigenvalue of the matrix. So from that, what you can say is that 0 is an eigenvalue of the matrix L. And as 0 is an eigenvalue, obviously the determinant will be 0, so the matrix is singular. So Laplacian matrix is a matrix which is always singular. We should keep that in mind. And if we have a weighted network or weighted graph, what will be the changes? So in place of 1 in the adjacency matrix, we will basically put the weight. So you can see that in place of the link, there is some weight that is assigned there, and that weight is reflected in the position. So let me consider a position I, say 1, 5. 1, 5 in L, if you can see, that is -2 because of the weight. Okay. If we have an unweighted graph like this, I would have -1 here. But again, that property of each row equal to 0 prevails here. So from this, what we can say is that this matrix, whatever the matrix, maybe an undirected graph, maybe an unweighted graph, maybe a weighted graph, the sum of each row will be equal to 0. So that is the takeaway. And here I would like to stop for a few minutes and try to evaluate some other properties of this matrix. Do you have any query up to this? You can ask. So I would like to stop a few seconds here, pause a few seconds, and I want to go to Laplacian to evaluate the properties. Am I audible? Is it all right?
Yes, sir. Able, sir.
Okay.
Dr. Shankar Chandra, sir, please switch off your video.
So now I am sharing my screen with a board. Can you see my board here?
No, it's not visible, sir.
Okay. Wait a minute.
Share the full screen, sir.
Okay. Yeah. So can you see my board now?
Yes, sir. Yes.
Oh, okay. Thank you. So being a person of maths, we are more comfortable in the blackboard or whiteboard rather than in the slides. Yeah. So basically, when I say Laplacian, say this is a graph. Say this is something like this: 1, 2, 3, 4, 5. So for this graph, the Laplacian will be a 5 cross 5 matrix. 5 cross 5 matrix. And in the diagonal position, it will be like 1, 3, 2, 3, 1. And in the off diagonal position, as per the definition, we have to check the connections. So is there any connection between 1 and 2? Yes. So I should write it -1. Is there any connection between 1 and 3? No. So this is 0. Is there any connection between 1 and 4? No. It is 0. Is there any connection between 1 and 5? No. 0. For 2 again, I will repeat that. 2 and 1, there is a relation. So it is -1. 2 and 2, obviously it's a simple graph. There is no loop. And 2, 3 is basically -1. There is a relation. There is a connection. 2, 4, there is a connection. And for 2 and 5, there is no connection. Something like that. And let me fill up the other entries here. So this entry will be 3, 1. So this is 0. 3, 2 will be -1. 3, 4 will be -1, 0. 5, 1 will be 0. 5, 2 will be 0. 5, 3 will be 0. 5, 4 will be -1. So this is the sorry, the fourth row is missing. Fourth row will be like 0, -1, -1, -1. I hope I am clear. Now you can see that sum of each row is 0. So 0 is an eigenvalue. Right? Okay. And also, there is another vital property of L that we can explore here with the help of oriented incidence matrix. So what is an oriented incidence matrix? It's a matrix which is not square. It may not be square, where we will introduce the vertices here, V1, V2, Vn, and in the column we will consider the links. So basically it's a n cross m matrix. Okay. And why I'm calling it oriented incidence? This is basically the oriented matrix, but there is a twist. What is that? If it's a directed graph, then the traditional definition of incidence matrix for directed graph will be considered. If the graph is undirected, we have to assign some orientation to the graph. For this graph, I can assign some orientation. Say this is the direction, that is the direction, that may be the direction of your choice. That choice is yours. You can choose any direction. You can orient the edges whatever way you like. And ultimately, you will have a matrix like this where for a particular edge, say this is your first edge, E1, say this is your second edge, E2. For edge 1, say E1, what I'll have? I will have two vertex. One that is 2, which is the starting vertex. I will put 1 here. And what is the end vertex? Terminal vertex is 1. So I will put -1 there. And for rest of the vertices, I would have 0. So you can see that in each column, I will have one entry equal to 1, the other entry will be equal to -1. Again, if I go to this, say this is my E4, 3, 4 link. So in E4, what I'll have? I will have the 3, 4 entry to be 1 and the 4, 4 entry to be equal to -1, rest of the entries will be 0. Okay, this is a very special matrix. And why I am defining this, or why this particular matrix is considered? Because if I call this matrix to be Q, then L is found to be equal to Q transpose. L is found to be Q transpose. So that is a very interesting result, that we can relate this oriented matrix with the Laplacian matrix in this way. Now, why this is so important? Because this will lead to something like this. So now if I consider for any non-zero vector x, what I will have? I will have X transpose Lx to be equal to X transpose QQ transpose X, which is equal to norm of Q transpose X whole square. So this is positive. And from this, what you can call is that L is a semi-positive definite. So this matrix is semi-positive definite because this result is true for any non-zero X. In fact, for X equal to 0, we will simply have equal to 0. No issue. But we are considering only the non-trivial case. But if we have a semi-positive definite matrix, what can you say about the eigenvalues? So the eigenvalues of L, all the eigenvalues will be greater than or equal to 0. So eigenvalues are non-negative. The eigenvalues of L are non-negative because of the fact that it's a semi-positive definite matrix. Right. Now, what we have understood from the definition and from the earlier result is that L is a symmetric matrix which is real, and eigenvalues are non-negative. This is first result. The second result is L is singular. So 0 is always an eigenvalue. 0 is always an eigenvalue. 0 is always an eigenvalue. Right? From this, what you can conclude is that if mu1, mu2 up to mu1 are eigenvalues of L, then I can write them in this form. Sorry. This is very interesting. I can write all the eigenvalues in this way. The smallest eigenvalue I know that will be equal to 0. But the interesting one is the second eigenvalue. The least non-zero eigenvalue is very interesting. And this eigenvalue is called algebraic connectivity. Algebraic connectivity. Okay. Why this is called algebraic connectivity? Because this will determine whether the graph is connected or not. So for a connected graph, what we'll have is that this mu2 will be non-zero. This mu2 will be non-zero for a connected graph. And the number of zeros, I mean, if mu1 is always 0, that's okay. But mu2 may be 0, may not be 0. If mu2 is 0, then what we can conclude is that Z has two components. So this is a disconnected network, disconnected graph with two components. If mu3 is also 0, then the number of components will increase to 3. Okay. So in this way, it is not very difficult to see that the multiplicity of 0, the multiplicity of this eigenvalue 0 is equal to number of components of the graph. And how can you show this? This is not very difficult. Let me give you some hint. Is that as we know that 0 is an eigenvalue, what is the eigenvector? The eigenvector is basically all n is equal to 1. Okay. Why? If I multiply L by U, that is something like summing up the rows, sum of the first row, sum of the second row, something like the entries will be like this, because the first row will be multiplied with this U, and I'll have this sum of first row, and I know that each row will be 0, sum of each row will be 0. So 0 corresponding to the eigenvalue 0, the eigenvector is 1 1 1. Now from the idea of linear algebra, what we can say is that if I want to get an eigenvalue different from 0, our idea is the idea is to choose an eigenvector which is non-parallel to u. So if we consider a vector which is dependent on u, something like this cu v, with this v I will definitely get 0 only. So if I want to get a non-zero vector, a non-zero eigenvalue, then I should choose something which is independent of V, linearly independent of V, or rather U. But here is a catch. The catch is that if we choose a linearly independent vector with a vector V linearly independent of U, that may not give you non-zero eigenvalue, because it will be determined by the eigenspace of 0. If the eigenspace of 0 is more than 1, then we will have more number of eigenvalues, eigenvectors, linearly independent eigenvectors. I am not going in detail into this, but just I want to highlight a few things, like if we compute this, this is nothing but norm of q transpose x squared, and this will be like xi minus xj whole square for all eigenvalues. So this is the result. You can check this result, and you can, this is not very difficult to check that if the graph is connected, then all these xi's are equal. Because you see, I will be say this is the graph 1 2 3, say this is a network 1 2 3 4 5 6. So for this is what I'll get x1 equal to x2, and for this is I'll get x2 equal to x3. For this is I'll get x2 equal to x6. Since there is a path between every pair of vertices, being a connected graph, all xi's would be equal. So if we consider the vector, the eigenvector x to be some, say x1 dot xn, then this will be something like c111. All will be equal to c. So xi's are equal to basically c. Okay, this is the scenario, right? Now, the next thing that we should know is the inverse. So these are very basic things. Just I am just giving you the highlight. If say lambda is an eigenvalue of L or A, whatever, then lambda inverse will be an eigenvalue of A inverse. We all know this. Okay. Similarly, in case of non-invertible matrix, what will happen? Non-invertible matrix, if we consider the invertible matrix, I mean the singular matrix, invertible matrix A, there will be some 0 eigenvalues. Obviously, for corresponding to this 0, I cannot have an eigenvalue. Okay, so in case of any generalized inverse, say like Moore-Penrose inverse, we will consider only the non-zero eigenvalues to compute the eigenvalues of the inverse, and the rest of the eigenvalues will be 0 itself, not its inverse. That is the scenario from the singular value decomposition. Okay, we'll discuss this when we have when we will encounter the Moore-Penrose inverse. Okay, and I think this will be enough to proceed. Let me check. If there is an issue, then we will come back. Okay. Can you see my screen now? Am I audible?
Yes, sir.
Yeah. Okay.
Yes, sir. Yes.
Okay. Okay. I hope this is clear. Up to now, I think whatever I have, introduced and discussed, these are very basic things. I hope all these things are very clear to you. Now we will try to figure out. So these are the properties, right? The L is square, symmetric, matrix of order n, where n is the number of vertices of graph. L is singular, where 0 is an eigenvalue. L is semi-positive definite. This is the result that we have discussed already. So these are some basic properties of Laplacian, and we know how we can obtain this and what is the background of all these statements. Okay. Now let me come to the Morey-Penrose inverse. So Morey-Penrose inverse is defined for any matrix. It can be a square matrix, it can be a rectangular matrix. This is basically a very, purely algebraic calculation of the inverse. Okay, this is one kind of generalized inverse, and that it is proposed by Penrose in way back in 1956, which is as follows: that if A is a matrix, any matrix, then there is a unique Z that will satisfy this criteria. And if the matrix is invertible, obviously the generalized inverse is equal to the inverse of the matrix. And eigenvalues of A again. See here you can see that if we consider the singular value decomposition, or if we want to consider the diagonal entries, there you can see that we have 7 and 6. So for sigma plus, we will have 1 by 7 and 1 by 6. What about the 0 entries? We will leave it as it is. Okay, and that will be the scenario because of the singular value decomposition that we have in hand. Okay, so this is the singular value definition, that if we have an inverse, then you can see that any matrix, here we are considering a diagonal matrix. In the earlier slide, in this slide, we are considering a diagonal matrix. So you may be confused by this formulation, that why this diagonal matrix case is only considered. Because if we are clear with the diagonal case, we will be happy to find the generalized inverse of any matrix because of the FD. Here you can see that we have a matrix A whose SVD is P sigma Q transpose. Then the pseudo inverse, generalized inverse, Morey-Penrose inverse, whatever you like to call it, will be Q sigma plus P transpose. So you can see that the matrix P and Q will simply be interchanged. Of course, the transpose of this matrix will be considered to find the inverse, but the key player here is the diagonal matrix that is present in the middle, that is the sigma matrix. Okay, and now I don't think there is any issue if we consider the trace of this A plus. So what will be the trace of A plus? So trace, we know that trace of a matrix is equal to the sum of the diagonals, and that is basically equal to the sum of the eigenvalues. So in case of A plus, or in case of any inverse, what will be the trace? The trace will be the sum of inverse of the eigenvalues, right? So if your A plus is non-invertible, singular, then we have to drop all those zero eigenvalues, because they are not going to contribute anything to the sum. Otherwise, we will consider all the eigenvalues but their reciprocals. Okay? So that is the test. Now let me go back to the business. I mean the basics of graphs. Okay? This is, I don't think there is any need of any introduction. Shortest path is basically the path with minimum number of edges, sequence of minimum number of edges. Okay? And all I want to say is that there is an idea of average shortest path or the maximum diameter of the graph. So that is basically the maximum shortest path. That is the diameter, largest shortest path. And average shortest path is the sum of all shortest path divided by total number of possible edges. That will be NC2 from annual randomized development. Okay. Now we are ready to deal with the network. So in a network, which is different from graph, is that in a network we may assign some kind of importance to the node. I mean, all the nodes in a network may not be equally important, like in graph. So how can you quantify that? That is a big issue. That is it possible that all the nodes are not equally important? If it is so, how can we quantify them, or how can you find out that which node is more important? So the first measure, or we can say it's a very raw measure, it's a very primitive measure, that is the degree. So degree will basically evaluate that how many numbers of neighbors are connected to this particular node. That means how many direct connections that particular node is having in the network. But that is not always true. I can give you some examples, because in some cases some nodes may be connected to very few nodes, but those few nodes are with very high degree of connectivity. So this is a very primitive way to quantify the importance of a node, but we are still considering it. The other one is the closeness centrality. This will determine that how close is the node to all the nodes. So basically it will evaluate all the shortest paths for all the pair of all the vertices from a fixed vertex, and consider the inverse of the sum of the lengths. That is the closeness centrality of a node. If the node is in a central position, this value will be maximum, because then length will be minimum. Okay. See, here we are not considering only length, but a sum of the lengths. So all the nodes has to be taken care. All the nodes have to be taken care. Now we come to the betweenness centrality. This is a very interesting measure. As I have told you, that you can see that in this particular figure, the node I is connected to two subnetworks or two subgraphs, but there may be some nodes in each of the subgraphs which will have many connections. But if we think of only I, we can see that it has only two connections. Only two connections. But from the earlier measures, like degree centrality, what we should conclude is that this I is not that important. But from a practical point of view, if we look at this node I, if we remove this node I, that will basically disconnect the graph. This is very interesting. So the importance of this node is not measured in the way it should be considered. Okay, so betweenness centrality is going to address the issue that some nodes may be very weak in connections, but their connections are very vital. And we call this kind of links to be bridge. Bridge means it's an edge, it's a link. If we remove that link, it will basically disconnect the graph. Or if the graph is already disconnected, it will increase the number of components. Okay? Then how can we address this? So between the centrality gives you a perspective to address this issue. What is it suggests is that consider all the shortest paths and put it there in the denominator. In the numerator, what we should consider is all those out of these shortest paths, how many of them are actually going through I? Okay, so this is a ratio between all pairs of shortest paths passing through I to all pairs of shortest paths. So I hope this is clear. If you need some explanation, then we will come back, or if you want to stop me here, then I'll be happy to explain. I don't think there is any difficulty to understand this. We are considering all the shortest path passing through a particular vertex I in the numerator. And here we are considering all the paths. Those paths from L to M may pass through I or may not pass through. But we'll consider all the shortest path from L to M. And in the numerator, we'll consider only those paths which will pass from L to M through this vertex. This is for a fixed pair Lm. But we have to sum up our all such pairs. And that will be our beginning circle. And this is a very, interesting result, an interesting notion, which is used, which has found many applications in real networks. Because sometimes what we have seen is not actually true. Though it has very less number of connections, but ultimately these connections are very, very important to maintain the connectivity of the network. Okay? Right. Now let me go to the next slide. Okay. The clustering coefficient. So clustering coefficient is basically a measure of a situation where, say, A is a friend of B and B is a friend of C. So what is the probability that C is also a friend of A? Okay? So if we consider a triplet, what is the possibility that it will form a clique from the theory of graph? When I say clique, that means this is something like this. This will be called a clique. So if you consider a triplet, what is the possibility that it turns out to be a clique? Here I is friend with 3, I is friend with 2. What is the possibility that 2 is also a friend of 3? If this happens, then what will happen to the network? All the nodes will be clustered around some points. So that's why it is called clustering coefficient. That means if the clustering coefficient is high for a vertex I, we should understand that around I, most of the vertices are clustered. Okay? Right. And sum of all this clustering coefficient divided by n will be the average clustering coefficient. So if the average clustering coefficient of a graph is high, what we should understand is that the graph is more connected. Friend of a friend is also a friend. So that's why in a simpler form, we can compute this C as 3 times of number of fully connected triplets divided by number of triplets. So number of triplet means it may not form a clique, but here we will consider only the cliques. Sorry, by clique I mean I have not introduced the term clique. Clique is basically, it's a complete graph with 3 vertices. Clique of length 4, then it will be a complete graph of 4 vertices. I mean, not a complete graph of 4 vertices, but it's a rectangle, some kind of a rectangle. There will be a cycle basically. Okay. Now, some statistical characterization of networks, degree distribution. So each degree will be noted down and they will be put in some form, but this is a very noisy kind of a distribution. So better to consider the probability in this way, where we have to find a cumulative probability distribution, where we'll think of probability of a node having degree less than equal to k. Sorry, greater than equal to k. That is the probability. And with this probability, this distribution of degree is known as degree distribution. Okay. And this is the probability, right? Probability data randomly choosing degree has k. Has degree k. And average degree is sum of the degree divided by n. These are some other measures. So what do I mean by sparse graph? You must understand this. Sparse graph is a graph where there will be very few links. There will be very few edges. Okay, that's why the average degree is very, very less than n. So most of the nodes will be having only 1 or 2 connections, not more than that. Now, these 2 networks that we are going to discuss, these are synthetic networks. These are very popular models, and many of you may know about these models. One is Watts-Strogatz model. This is a small world model. So this is the first model which suggests that if we allow a network to happen in a real world, the network or the participating nodes has a tendency to make it a small world. I'm giving you an example. Suppose you are allowed to choose any of the nodes in a network. Say there are 5 friends and one is having more number of connections, and a new node is coming to picture. A new node comes into picture, then he will basically tries to minimize his average distance from all other nodes. So what should be his first choice? He will try to connect to the high degree node. So this is a process where in case of a regular graph, it is well defined that each of the vertex will have, say, 2 number of connections, 3 number of connections. But in a small world, these connections may be broken. We call it rewiring. So this wire may be broken and that may be connected to some other vertex, like this. Okay. Here, you can see that this node is, this particular link is actually broken from this and it is connected with that. This is called rewiring. And if we allow complete freedom, then we may expect any number of connections to any other vertex. This is a very highly random situation. This is usually not happen. So we have a regular graph, we have a random graph, but in real world, this is more likely to happen. That we will have some kind of randomness, but there will be some distinct criteria based on which this connection will be preferred. And you can see that any Watts-Strogatz model, any small world network will have these 2 criteria. The one is the large clustering coefficient. We have already defined. Clustering coefficient is what? It will be clustered around some point. So basically, it will lead to what? Small world. And shortest average path length. Okay, so the path length will be reduced. So both these criteria will lead to short path length will be less, and clustering coefficient will be high. So this criteria will lead to what is called small world. And if you are interested, there is a very interesting experiment that was done in 1960, in fact, that is called Milgram experiment on small world. And because of that, the idea of 6-point separation comes. So, if there is anyone from computer science, they can elaborate these things very well. I mean, these are very relevant notion that computer science is used to talk about. Okay, so we should be interested in the graph theoretic notion. The graph theoretic notion are that the clustering coefficient will be high and the shortest path will be low, as expected. Okay. Also, we should not be confused by this model with the model of another kind, that is called the Bharali-Albert model. This is also known as preferential attachment model or rich-get-richer model. Rich-get-richer model. So this is the growth of a model is described by this particular model. The growth of any network is basically described by this model. So why the growth is taking place, some vertices will be added to the network. Then what will be the choice for this vertex? If this vertex is allowed to be connected with any of the vertices, then what should be his choice? The probability that he will choose the most linked one. So that's why the probability is proportional to, I should say, to the degree of a vertex. So rich-get-richer approach. This is called rich-get-richer approach. The rich vertex will now get richer. The more connections you have, there is a possibility that you will have the next connection to you only. Rich-get-richer, because the newly coming node will prefer this mostly connected node as the attached. So that's why it is also called preferential attachment. Okay, and ultimately this distribution comes out to be a scale-free distribution. Scale-free. That means the probability is k times gamma. Probability is proportional to k to the power minus gamma. So gamma is a constant. In case of Bharali-Albert, this is 3. We can think of some other number. Now, let us observe this network criticality from the perspective of probability. So, what is a random walk? Because before that, let me give you the transition idea. So, this is the adjacency matrix. This is an adjacency matrix. There is nothing to explain, but here this is transition matrix. So, you can see that this is the vertex. So, now if the flow is here or the random walk is here at this point, what should be his next step? So he has two options. Either that walk may go to this particular node or this may go to that particular node. Then from the theory of probability, what you can say is that the probability that this will go from the ith node to zth node is half. This is the transition probability. And using this, we can define the network criticality. So in a network, if we define the betweenness to be something like BL, then this tau is the network criticality. This tau is the network criticality. Here you can see that though I am writing this to be for L, this ratio of BL by WL will be a constant ratio. That's why tau is independent of link position and tau is a global quantity. This tau is termed as network criticality. It is based on betweenness divided by weighted. So WL is the weight of the link. So in the earlier, say here you can see that what is the weight, basically weight of the link. If we, here the weights are 1 1, that's why this is 1 plus 1 2. So there you have 2 in the denominator. Okay, and obviously the smaller value of tau means higher level of robustness, as the name suggests, and from this theory also, if tau is high, that means the betweenness will be high. So there will be a dependency on the link. Okay, if tau is high, that BL is high, that means the dependency on L will high, because BL will define that how important, how critical is that link L to keep the network connected. Because most of the, now as the BL is high, what you should understand is that most of the shortest path are actually going through the link. Okay. So it can be used to quantify the resistance of a network to the unwanted changes in the network topology, and you may check the Tisgadam and Leon Garcia paper to understand its applicability as a measure of resistance or robustness. Okay. Now here we have studied the network, the network measure, and we have found that this network measure is actually 2 times of what is called the effective gap resistance. So L plus, which is the Merov-Monroe's inverse of L, is equal to L plus J by N to the minus 1 minus J by N. So this is a very standard result. You can find in any book of metric theory that L will be something like this. Now, if we think of L plus J by N, what will be the eigenvalue? I know that all the eigenvalues of L will be, say, I know the eigenvalues of L. It will start from 0, then you will have mu2, then you will have mu3 up to mu1. What about the eigenvalues of J? So J is a matrix with all entries equal to 1. All entries are equal to 1. What will be the eigenvalues? You can see that the rank of the matrix is 1 only. Right? So there can be only one non-zero eigenvalue. And what is that? That is basically n, because sum of each row will be n for J. And what will happen to J by n? The only non-zero eigenvalue will be 1. From this, what you can say is that the set of eigenvalues of L and J by n will be, for L you have eigenvalues 0, mu2 up to mu1. For J by n, you will have eigenvalues 1, 0, 0, 0. So if we sum them up, we will have eigenvalues of L plus J by n will be 1, mu2 up to mu1. And if we consider the inverse, so this will be like, what will be the inverse? So I have to consider the reciprocal of this. Right? Also, you see, how can you find the eigenvalues of two matrices? I mean, sum of two matrices if the eigenvalues of the matrices are known. We have to check whether they will commute with one another or not. I mean, if A has an eigenvalue mu, B has an eigenvalue lambda, then A plus B will have an eigenvalue mu plus lambda if and only if AB is equal to BA. And this is going to happen for these two matrices. This is your A set, this is your B. So using all this idea and some simple manipulation helps us to find that the test is actually 2 times of that. Okay. And this result, I am just omitting this result for the time being. Okay. Okay. Now the motivation for our new major. See, I have two graphs here. One is Z, the other one is Z prime. And the weights are selected in such a way that their tau will be same. So from the global measure, that is tau, what we can conclude is that both the networks are equal from the point of view of robustness. From the point of view of robustness, we can call these two graphs Z and Z2 be equal. Sorry, Z prime. Because why? Because tau is same. But if we look at this graph Z, and if we remove one edge from this, will it be disconnected? No. But now if we look at Z prime, if we delete one edge, what will happen? It will disconnect the graph. So you can see that from the very observation of the graphs, we can say that this is more robust. This is more robust than this. But that is not captured by tau. So this is our motivation example. The tau can... Yes, pardon me. Is it okay? Okay.
Yeah, okay.
Madam forward చేసింది కౌంటర్ మళ్ళీ మోడిఫై చేశారు అంటే బాగా
Yes.
Okay, sir. Go ahead, sir.
Okay, shall I continue? Yeah.
Yes, sir.
So from the perspective of robustness, what we can say is that clearly the graph Z is better than Z prime. There is no doubt about it. Okay. Then we try to address this issue. So what we have found is that if there is some edge like this one, which is actually a breeze, the presence of a breeze is actually making that particular network or graph more vulnerable to changes. If there is a bridge, if that bridge get, if there is some changes in that particular link, the entire dimension, the entire topology may change. So from the perspective of robustness, what we should understand is that the presence of a breeze is very important. We should to capture that particular effect of the breeze. So based on these observations, what we have supposed and what we have proposed is that rather than using a global measure, we can think of a local measure. That is your tau e. So now we have introduced a local measure, that is tau e, which is different for different link. So the contribution, this will basically evaluate the contribution of a link to the network from the perspective of robustness. What is the importance of that link for the robustness of for the well-being of the network? And tau e denotes the network criticality. We are using the same measure, network criticality, but for the reduced graph. So we will also evaluate the criticality of the reduced graph. Here you can see that this tau e is a local measure. This is local in nature. And this is the theorem that we have proposed, that if E is not a bridge, then this will be this is a lower bound for tau e. And this will come from basically from the idea of interlacing and the HM-GM-AM relation. Okay. So tau e will be something like this, twice n sum of 1 by mu y, where mu y are the eigenvalues of the reduced graph. And from HM-GM we will have this. So we will consider the extreme. Forget about this. We will consider these two. From this we will have this. Now you can see that this is sum of mu y. Then sum of mu y will be what? Sum of mu y. This is a trace of the eigen of the matrix L, because these are eigenvalues of L. What about trace of L? Trace of L will be the sum of the degree. Sum of the degree will be equal to twice the number of edges. Here in this case, the number of edges of Z E. So if the number of edges for Z is m, this will be m minus 1. Hence we have this result, m minus 1. Okay, because we have delete one edge here, isn't it? We have delete one edge, so that's why the number will reduce to m minus 1, twice m minus 1. Okay, and this is another result of tau based on kappa. Kappa is a tree number. Tree number is basically kappa is tree number is the number of spanning tree. I'm not going to go into detail to this notion spanning tree. If you are interested, you can check that particular paper, or I will let you know what is the paper, and or you can just check any standard book. There you can find it, the idea of tree number. Or rather, if you are interested, I can suggest one book that is of Norman Biggs. Norman Biggs, algebraic graph theory. There you can find this notion. Right. Another result, this is important. Now we are going to deal with tau e, and we are going to compare tau e with tau. This is the motivation, and this is the groundwork that we need to define the measure. So one result is something like tau e by tau will be always bounded by maximum of the ratio of the successive eigenvalues. And just keeping this result because this is not that important to define our measure. Rather, we will go to this result. Okay, here you can see here I am using again the interlacing property of graph because it's a reduced graph. I can use the interlacing property. Anyway, so if we now compare the value of tau e with tau, there you can see if we reduce the if we delete an link, then we'll always reduce or enhance the criticality. So if you remove one option, if we remove one edge, one link, that will increase the criticality of the network. But that is not the case if E is a bridge. If E is a bridge, that new criticality may not be greater than equal to the old one, but there is a quantity based on which we can compare. Otherwise, this is not strictly greater than equal to tau. It may be less than that, but this quantity will make sure that this sum of tau with twice n by mu will be always greater than. So this result is very important, and this is the foundation of our measure. So this is the measure. Now I am going into the measure. So the measure that we have proposed. This is an average network functionality measure. Here you can see that if tau a is greater than tau, then this is positive. So if this is positive, so this value will be 1, and this ratio will come into picture. Otherwise, what will happen if this is negative, then this will be 1, this will be 0, and this will come into picture. Whatever be the situation, from this theorem, we can say that each of these ratios are actually less than 1. So if I sum them up, for every edge, I can get maximum m here. This quantity, this summation will always be less than equal to m. So I am normalizing by m to keep it below 1. And that's why this tau is in between 0 and 1. Sorry, eta bar is in between 0 and 1. This eta bar can be considered as a measure of functionality of network. We propose that, and we have tested this measure in two synthetic networks that we have already discussed. One is one-stroke network, the other one is Bharali-Alpha network. And for computation process of this measure, you can consult this book, this particular paper. Okay, so this was a very theoretical way to present eta bar. But if we want to go into detail of the computation aspects of this, of course, there will be some other issues of that using data structure and complexity. So this paper has addressed this issue, how to calculate this eta bar efficiently. Okay, and Now we test this measure eta bar in these two networks, Schwarz-Strogatz and Bharali-Albert. For different rewiring probabilities, I have already told you P is the rewiring probability and different size of seeds. Seeds means the starting number of vertices in the evolution of the network. And the results obtained for various number of nodes, starting from 50 to 300. Okay. Why I have not considered 1000 number of nodes? Because of the computational complexity at that time. But now with this paper, we can also extend this results to say 5000 number of nodes. Now the complexity issue will not be there. There are some manipulation that can be helpful to find these networks even for. Of course, we can do that, but that is time consuming. That's why we have restricted ourselves to 300. And what we have found is that in case of Bharali-Albert network, the average path length increases approximately logarithmically as the size of the network increases. And in case of Schwarz-Strogatz network, as the rewire probability increases, the connections with neighbors break down. You can see that with the increase of P, the neighborhood connections are rewired, disconnected and connected to some other nodes. Here in this network. Here you can see with the increase of P, the neighborhood connections are disconnected and we establish some other connections. Okay. Yeah. So in case of both the networks, one can expect that the functionality of the network drops down as the size of the network and rewiring probability increases. That should happen. And this property is actually reflected in our measure. So that's why we say that this measure can actually be considered as a measure of functionality, because it captures the very essence of functionality in itself. Okay. The results of the comparison between the average functionality, and also we have compared this particular measure with various other graph measures like average network functionality, clustering coefficient, average betweenness. And what we have found is that in case of both the networks, eta bar is bounded by average, so average betweenness, and there is clustering coefficient or eigenvector centrality. Here is it is sandwiched between these two, eta bar. Which is because of the fact that with the increase of size of the network, average centrality increases very rapidly. That's why it will go up. Whereas the rewiring edges needs to break down the cliques with the neighborhood. So if cliques break down, that means it will reduce the clustering coefficient. That's why the clustering coefficient will come down, and eta bar will be in between these two. It will be sandwiched by clustering coefficient and average betweenness. Yeah. And in both the networks, we also see that the clustering coefficient and eta bar is highly correlated. If one increases, the other one also increases. Which is because of the fact that the presence of more cliques reduces the chance of an edge to become a bridge. You see, if there is a clique, deletion of an edge, deletion of a link, or removal of a link will not lead to disconnectedness. So if we have more number of cliques, the possibility that an edge becomes a bridge will be less. Eta bar exhibits negative correlation with eigenvector centrality in Schwarz-Strogatz network and betweenness centrality in the Albert. So they are positively correlated with this particular measure is positively correlated with clustering coefficient and negatively correlated with eigenvector centrality and betweenness centrality in either of the network. In Schwarz-Strogatz network, it's also visible that the degree distribution among the vertices is closely homogeneous, which explains the reason why negative correlation happens. Okay, and eigenvector And again, in Barabasi-Albert model, it is based on a preferential rich get richer effect. So an edge is most likely to attach to a node with high degree. So if a link is removed, that will not immediately break down the network, because you can see that most of the links will have many number of degrees because of the rich get richer. So it reduces the chance of an edge to become a glitch. Hence, we can expect a negative progress. So for application of this, we considered two papers, one of Hawk in 2009 and Tang in 2020. And if you want to see some other applications, you can see this paper of us published in 2019 and 2020, and this World KGN et al. Published in 2012, and the references there. But for this discussion, I have chosen these two papers. One is Hawk, the other one is Tang. Hawk is a paper where cyber security issues is addressed, and Tang is a paper where a new algorithm is proposed based on a blended criteria of local and global nature. So these are the papers. One was published in this, the other one published in that. Okay. So in the first paper, they extend our analysis and they use the same measure for random cyber attacks on energy delivery system. Let me tell you that there can be, if we want to divide the kind of attacks, there will be two broad categories. One, where the random failure should occur, and the other one is the intentional attack. So in intentional attack, the probability or the vulnerability of different nodes will be different. A node, an important node has more possibility to be attacked in case of intentional attack. In case of intentional attack, an important node will be preferred. But in case of random attack, all the nodes will have same probability of being attacked. Okay, so they have considered the random case in the energy delivery system, and the author assumes that removing certain links in the server attack incident as deactivating some control functions and services, which attackers achieve by eliminating the logical connections. So some links are randomly removed, and they have checked the response of the network based on the measure proposed by us. Okay, whether the functionality prevails or the functionality decreases, functionality increases, something, so on and so forth. So, and they call it critical system functionality. So critical system functionality is the level of system functionality maintained by an energy delivery system in case of an adverse situation. So in their work, the authors address the research gap regarding the relationship between the cyber resilience and the system behavior. So earlier, the cyber resilience is not, it's a one-dimensional affair. They will basically try to figure out that how the the network will behave if there is some attack. So here they have blend this cyber resilience issue with the behavior of the system during a cybernetic event. Of course, they have only considered the random kind of attack. So the intentional kind of attack can also be considered, and they have compromised with many control functions in their discussion, in their paper. So in a future model, we may consider different control functions, some other control functions to check the different level of utilization of those control functions. So this is one aspect, future aspect, that we can think of more control functions and try to figure out that what will happen to the network if we consider more number of control functions. One aspect is there. The other aspect is here they are considering the random methodology. So they are not concerned with the importance of the node or some intentional attacks. But we can also take that part into our future course of action. Again, you see that in tau and tau e, tau was a global measure and tau e is a local measure that we have proposed. But Tang have extended our idea of link importance based on measure, and they try to balance these two idea. That they want to balance the idea of local with global. And what they have commented is that it is difficult to balance the local and global aspects for existing mainstream algorithms. So they have proposed an algorithm that is taking care somewhat, I mean, it is a midway between local and the global aspects. So in their algorithm, they have considered some propagation style, like in in local measure, we consider only the direct, like immediate kind of reaction or immediate impact. In a global measure, we consider the overall impact. But in their algorithm, they have proposed that there will be some k that will determine the propagation style. That how much, what will be the length of paths that will be considered for effectiveness. Okay, but there is obviously a complexity in calculating this k. What will be the suitable value of k? That is one issue in their algorithm. That how can you choose k? For k equal to 1, obviously this will be local. For k equal to say n, that will be, or whatever may be the diameter, that will be the global aspect. But how can you choose a suitable value of k? That will give you a better algorithm, as well as the complexity of the, or the runtime of the algorithm will also reduce. So there is a, you can say, that pre-processing time that will be involved in deciding the value of k. That is one issue. And they have measured the features of this algorithm in some real networks. That is another good aspect of this paper, that they have considered real networks rather than some synthetic network. So one drawback of our paper that you can say is that we have theoretically done it. That's why we have considered synthetic network. And in our later papers, I mean in the paper published in 2019 and 2020, of course we have considered some real networks. But in this paper, they have considered some real networks. So that will give you a better picture of the measure. And they are very much agree with that, with the fact that the aspects of local, it is very hard to mix with the aspects of global. This algorithm is called the WKTN algorithm. And this is proposed for only weighted undirected graph. So one future aspect is that you can improve that algorithm for directed network. One aspect is that, because there are so many networks that we can think of in real world which are not undirected, one-way connection. Okay, and also the other aspect is that you can think of what will be the value of k. How can you suitably choose k with least complexity? Because you have to address this issue of time complexity there. If we take too much time in fixing the value of k, that algorithm will be very costly. So these two aspects that we can address. Surely these aspects are basically for computer scientists. I'm not an expert in this line. I mean the time complexity and all these issues. So what I can say is that yes, this can be done. Maybe it's a possibility, but I don't know whether it can actually be done. But one thing is for sure is that I can tell you that this algorithm can immediately be modified or improved for directed network. So this is a very immediate future problem that we can consider. So with this, I would like to conclude here. And in this talk, we have basically introduced a novel measure of functionality based on a very well-studied measure, that is network criticality. And we have addressed the issues from the perspective of graph, and also some applications of our measure are reviewed. Two future tracks of research in this topic are also highlighted. So you see, a study of the effect of different catastrophic disaster like floods, any natural calamity, or targeted attacks on networks. It is found that these networks are these theories are very important if you want to deal with this kind of catastrophic disaster. As the restoration of other networks basically depends on transportation network, so it is even more important to address the transportation network, like airport network, like road network, like railways network. So all these networks are actually very important. One, to ensure the existence of a connected road network for the operation of the whole society. The second one, we have to stop any disruption that makes partial or complete failure of road network. Then only, or transportation network, then only the other networks can be run without any disruption. So if you want to figure out that which network, of course, all the networks are important, equally important, but if we think of from a very layman perspective, that these transportation networks are very much important for a, smooth running of a society. And of course, the biological networks are equally important, because some of the issues which cannot be dealt by the biological scientists, they are actually solving by computational biologists, which are actually nothing but computer scientists or network scientists. So with this, I would like to conclude the talk. And these are some references. You can go through the references, and I'll be very happy if you drop some mail in this mail address. This is my mail address. You can drop some mail at this Bharali@dibrugarh.ac.in. And this is the paper that is where the network criticality is discussed. And the paper of Ellen Ware, this is the paper where this network criticality is actually related to the Laplacian spectra of graph. Thank you for your attention. I hope I can give some idea about the work and the area of research, and I'm happy to have questions from you.
Yes, participants, any questions?
So there may be two possibilities. One is I am not that good enough to explain the thing. One possibility is that, and the other possibility is that you may need some time to digest the thing. So in that case, I will be very happy if you drop some mail. Okay, I will definitely reply them. You may not have an immediate question, of course, right? You may have some questions which may arise in your mind. You can drop a mail. I will be very happy to address. Yes, I can see some. Dr. Asutosh, I think you are mute.
Please
You are
unmute, sir.
mute yourself.
We mute it. Yes, Asutosh sir.
So
You have a question, sir? You are not audible, sir.
There may be some issue in the network.
Just wait, sir. Yes, sir. Sorry, sir.
Oh, okay. Yeah, now you are audible. Yes, please.
Sir, I have one doubt. I forget that slide name, but one slide I have seen. There is one thing is there, a transition matrix. About I want to query about transition matrix, sir. So please, if possible, can go to that slide. I don't know. I forget the slide number.
I don't think I have used the condition matrix here.
My voice is audible or not, sir?
Yes, your voice is audible, but I don't think that I have used the condition matrix here.
Yeah, transition. Sir, you talk about
transition matrix. Okay, transition matrix. Right.
Yeah.
Okay. Yeah. Tell me.
That slide, sir. I forget the slide name.
Yeah. I can explain that. Yeah. Okay. Yeah. Audible? Am I audible?
Yes, sir.
Yeah, okay. Suppose I have a directed graph like this. Okay, I have a directed graph like this. And I am talking about a walk. That means there is a transition from one vertex to the other. Suppose the walk is at this place, at this vertex, I. And this is the zth vertex. So if there is no way, from the perspective of probability theory, what you can say is that what is the probability that the next step will be at J?
Sorry, sir. Sir, some technical problem is there. I think some technical problem is there because I am not listening, sir, fluently. That's why I cannot listen your voice, sir. So please, sir, tell me.
Okay. Now can you hear me?
Yeah. This is
Can you
audible,
hear
sir.
me?
Yeah.
Okay.
Yeah. Yes, sir.
Yeah.
Sorry. Yeah.
So basically,
Asutosh sir,
this is
keep
a
your video
probability.
switch off. Switch off your video, sir. Sounds will be clear.
Okay, sir. Thank you, sir.
So you can see that if we consider a random walk, suppose it is at the point I in a time frame t. What will be the probability that it will be at the point j at a time interval t plus 1? So you can see that there are three options. If you are at this position, being a random walk, I can go to any of this node. I can go to this node, I can go to that node. So what is the probability that I will go to this node is 1 by 3, right? Because these are the three options and I am choosing this one, right? Am I clear? So that is the transition probability that I am using. So that's why in the transition matrix, the ith entry will be 1 by 3. But it is the probability that the random walk will go from I to j. If it is a weighted network, something like this, some weights are there, W1, W2, W3, then this probability will be what? W1 divided by sum of Wi's. Am I clear now?
Yeah. Okay, sir. Okay, that is fine. Sir, but sir, sir, audible my voice or not, sir?
Yes, I can hear you. Yeah.
Sir, can I apply? Or use this transition matrix to a stochastic process?
Yes, this is actually, in fact, from the stochastic process. Here, you are right. This is the
Okay.
same matrix that we are using in stochastic process because it's a random walk, right?
Okay, sir. Okay, fine, sir. You have
are
to
right.
show.
You are right. You are right.
Okay, sir.
I intentionally dropped that word because that may lead to some other queries. I intentionally
Okay, sir.
dropped
I
that.
have one query more.
Yeah.
Excuse me, sir. Sorry, sir. One question. I have one doubt. Second. Uh, Sir,
Okay.
one slide you have to show uh, matrix will be 3 by 3 is there. That is the square matrix you can take. So if you can go through that slide, sir, I forget the slide number. When I listen throughout your lecture, but I am forget that slide name. So after seeing
Okay.
your slide,
The
one
transition
slide is
matrix.
there.
The transition matrix.
You have to introduce. Yeah, transition. I talk about the only transaction matrix.
Okay. Okay. Yeah.
So there is a matrix 3 by 3 matrix, that is the square matrix. If you can take, if you if
Yeah. Yeah.
I want to that is this is my
Yeah.
yes,
I
sir,
am right.
this is my thought.
Yeah. 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 Sure. Yeah. Yeah.
Yeah,
Next
sir,
slide.
if
Yeah.
we can yeah, this is this possible to take, sir, n by n matrix, okay, and to move to the uh, stochastic process through uh, Hurwitz condition. Yeah, okay, sir, fine. Okay, fine. So
So
look at the
you are
both the slide.
basically asking whether I can use a. uh, So you are
Yes, sir.
interested to know whether I can use a non-square matrix here or not, isn't it?
Yeah, yeah. Not a square matrix. I talk about the not M by N order.
No,
That is not
you
a square
cannot
matrix.
use. Yeah, you cannot use non-square matrix because you see here we have the vertices. Again here in the columns we also have matrices. I mean the vertices. So this is like n cross n matrix because the transition is from vertex to vertex.
Oh, okay.
So it has to
Okay,
be
okay, sir.
square.
Okay.
Right.
Okay.
Right.
Okay,
Okay. Yeah.
okay, sir. Thank you.
Thank you. Is there any question? Any more question?
Any more questions, sir? No, I think no more questions, sir.
Okay. Thank you, Dr. Uh, Buddhadev, for the opportunity. And thank you, participant, for your patience hearing. And I will be very happy if you drop a mail regarding any query. At least you give me some feedback. I'll be very happy. And yeah, thank you very much.
Okay, sir. Welcome. Welcome, sir.
Thanks for accepting our invitation, sir. And thanks also for such a nice presentation and session. Very informative session, sir. Thank you, sir.
Thank you. Thank you very much. Bye.
Okay, sir. Bye, sir.